In this video, what we're going to try and do is determine whether a cylindrical storage tank with given conditions can fit in a particular warehouse. Then if it can fit inside that warehouse, we're going to try and determine the least possible cost of constructing it. So we have a wish for a cylindrical storage tank that has an overall capacity of 1,000 meters cubed. But we need to fit that cylindrical storage tank inside of a room. We'll assume that that room is a rectangular prism, and that room has dimensions of 12 by 15 with a height of 11. So we're taking this cylinder and we're placing it inside of this room, and we're hoping that our capacity can be at least 1,000 meters cubed. Well, if we were to maximize the radius of this cylinder, we would see that the maximum radius possible to fit inside the room would be 6. The reason being, since it's a circle, we see that the maximum possible diameter of the circle is 12 because the smaller of the length and the width is 12. So that's the maximum possible diameter, meaning the maximum possible radius is 6. So our maximum radius is 6. Our maximum height is pretty simple to see. We see that the height of the room is 11. So the maximum height is going to be 11. And so what we need to do is determine if, given the maximum radius and given the maximum height, could we in fact even fit the cylinder in the room? Well, if we determine the volume of a cylinder with a height of 11 and a radius of 6, we would get pi r squared h equaling pi times 6 squared times 11, and that would be equal to 396 pi. Well, 396 pi is in fact greater than 1,000. So what that tells us is we can actually fit the cylinder that we want inside that room. And we're going to have a little bit of room beside the walls. We won't have to maximize each one of those dimensions to make it fit. There's going to be a little bit of wiggle room on the sides and presumably at the top as well to make this fit. Okay, so is it possible for a tank of this capacity to fit inside the warehouse? The answer to part A is yes. So now we say if fitting the tank inside the warehouse is possible, determine proportions that minimize the cost of the steel. Well, part A also is requesting of us to determine restrictions on the radius. So we'll get into that right now before getting into part B. So looking at part A, we see that the maximum possible radius is 6. Again, that's because this 12 and this 15 are both restricting what the diameter of that cylinder can be. Since the 12 is smaller, then that's actually the one restricting what it could be. The maximum diameter is 12, meaning the maximum radius is 6. So the maximum radius is equal to 6. However, we also know that the maximum height is 11. Well, if I tell you that we have a cylinder with a volume of 1,000 and I maximize, I know that 1,000 is equal to pi r squared h. If I maximize that height right here, I will be minimizing that radius. This is a phenomenon we've seen happen with a lot of our domain analyses where we have two different independent variables. And in order to determine the minimum or maximum of one, we use the inverse relationship to our advantage and determine the maximum or minimum of the other. So in this case, to determine the minimum possible radius, we're going to maximize the height and determine what the corresponding radius would be. So if I let the height be its maximum possible value of 11, then I see that 1,000 over 11 pi is going to be equal to r squared, and that would mean that r will be equal to the square root of 1,000 over 11 pi. Okay, so given that the radius is minimum is 1,000 over 11 pi square rooted, we see that that's roughly 5.38. So we see that to fit the cylinder in the room that we have, the radius will have to be somewhere in between 5.38 and 6. Now, let's determine the cost, because that's what we're trying to do in Part B, is determine the minimum cost. Well, we know that the cost is going to be 100 times the area of the base, because the base is using sheet steel that costs $100 per meter squared. And the top is sheet steel costing $50 per meter squared, so it's 50 times the area of the top. And then it's 80 times the area of the sides. Well, the sides of a cylinder, it's really just a rectangle wrapped around. The top of that, the top length of that cylinder is really just the circumference of the circular top, which is 2 pi r, and the width is just h. So we have, instead of saying $80 times the area of the sides, we can say 80 times 2 pi r. Now, a little bit more obvious to see than that one is that the area of both the top and the bottom of the cylinder will be pi r squared. So our cost will be 100 times pi r squared on the bottom, plus 50 times pi r squared on the top, plus 80 times 2 pi r h. Okay? So when we collect up those like terms, we get 150 times pi r squared plus 160 times pi rh. We only want one variable on the right-hand side, and we know that the volume of this cylinder is 1,000, so that means 1,000 equals pi r squared h. Well, if 1,000 is pi r squared h, then 1,000 over pi r squared is h. So instead of expressing our cost as we did there, we can sub in for h this expression of 1,000 over pi r squared. And when we do a little bit of simplifying there, we get a fraction, but then we can simplify it. We see that our cost function as a function of r is really just 150 pi r squared plus 160,000 r to the negative 1, where r needs to be somewhere between 5.38 and 6. And obviously we're using some decimal approximations here. Well, now C prime r equaling 0 means 2 times 150 is 300. 300 pi r minus 160,000 r to the negative 2 equals 0. So 300 pi r equals 160,000 over r squared. If we multiply left and right both by r cubed and divide left and right both by 300 pi, we get r cubed is 160,000 over 300 pi. And that is roughly equal to 5.54. Well, if you recall, our domain for r was any value between 5.38 and 6. So 5.54 fits right in there. So now we just have to go back to our original cost formula that was fully in terms of r and plug in the values of 5.38, 5.54, and 6. And we see we get costs which are actually relatively close to each other, but if we let the radius be 5.38, our cost is $43,379 and change. If we let the radius be 5.54, our cost is slightly less, $43,343 and change. If we let the radius be 6, our cost is a little bit more than the other two. So the minimum cost possible will be $43,343.94 approximately.